Depending, which subject do you choose?
Huh?
Topics.
You mean at school?
Yeah, do you want to solve problem solving or you want to go through? Yeah, problem solving, yes. When will be your exam, by the way?
It's a data test, so it's not knowledge.
Oh, it's data test. Okay, it's not knowledge. It's just dealing with errors and uncertainty. Okay. Modeling, regression. Okay. Kepler's first law. Yeah. So Kepler have 3 laws. Kepler have 3 laws, right? Mm-hmm.
Yeah. Can you explain them, or do you want to do the whiteboard?
Oh yes. Okay. I just we can use textbook because it got printed text as good. So the before Galileo, before Kepler's, and we know that perhaps the Earth is orbit about the Sun, but most people in his time still believe that it is Sun orbited Earth. So there were a few people who actually seriously consider that the sun is at the center of the solar system. So Kepler is one of the leading observers. He actually didn't do much. He just focused on. Of course, he's good at math because eventually he proposed 3 laws. So basically, if you go to the diagram, probably talk about some diagram. So the diagram says that can you see that that's very good. In math, we have see that conic, right? Conical graph that includes circle, which is when this cutting plane is perpendicular to the axis, it becomes circle, right? But in general, if the angle is not it's not the plane is not perpendicular. Have you studied how to study the direction of plane? We use vector. Do you use it? Not yet.
No, not yet. No.
I think so. Basically, the direction of plane can be used by direct vector. Can you see that?
Yeah.
So that director will have, in this case, if they have angle. So this is a symmetrical axis of symmetry of this cone upside down. So therefore you will see the angle here. So whenever you see that, you see the ellipse. Ellipse is in general, so that's because this angle is not equal to 0. But if the angle equal to 0, you got a circle. Okay, so of course to start with, that most people, well, even people, I think Kepler is the first person who proposed this idea. But to start with, people just consider that the orbit of each planet is just a circle, right? It's quite reasonable, actually very close to a circle. But according to his observation, Kepler discovered that it is not a perfect circle. Actually, he proposed that it's actually an ellipse. See, it sounds very. So basically, we in the high school levels, we don't deal with this problem. But his noise can be studied, and especially when we approximate the ellipse as a circle, then you can use Newton's law for the uniform circular motion. So basically, they're dealing with that. Of course, then when the orbit, when different planets orbit about the sun, presumably they have different velocity, right? It's constant velocity. Whereas Earth is the sun. It's Earth. Oh, this is Earth-centric. That is Earth-centric. That's old-fashioned. So it's relatively speaking. So the time for the sun orbit about the Earth, like it's different, right? It's different because we saw the sun every day. So I don't know why they still use this Earth-centric. It's Earth-centric model, and it's actually out of date. Can you scroll downward? Kepler's law is not applied for the Earth-centric. Yeah, that's circle. Yeah, that's right. That is more. So the Kepler's law is that because it's ellipse, right? The ellipse, then they got 2 forks, like a forks, right? And there's folks, and therefore he said, well, that is general case because do you know what? This this also can eventually reveal even go to the comet. What is orbit of comet? Can you imagine? Comet.
And ellipse.
No. Now, how to cast it actually is not ellipse, is like this. Like, like, can you guess what's that?
Oh, okay, yeah. That's
Parabola. Parabola.
parabola.
Parabola. It's parabola. So you can see that's a special case that for the comet. But for the Earth, for any planet orbit about the sun and its ellipse. So ellipse will have long, basically have long races. Have you studied the ellipse in math? So you have a main axis, and that's called A, that's called B, right?
Yeah.
Do you know the formula for this ellipse mathematically?
No.
X square, as that is A square, A square, and plus X square B square, right? There's a Y, sorry, Y, X, Y. Well, this is a hypothesis that eventually be can confirm. Can you say when did he actually do it? Oh, you see that also a failing. This basically as shortest distance, is longest distance, okay, perihelion. So it's a failure. That's just represents the shortest and longest distance, right? So that only happened in ellipse, right? But for this, because for the circle, it should be exactly the same.
Yeah.
Okay. Well, this is just history, okay? Not yet. So not yet. Go to your. Can we go scroll down there to see what we can learn? Kepler second law. Oh yeah, first law already. Yeah, his first law just said, well, the orbit is ellipse. It's not a circle. Okay. It's very close to a circle, but not the circle. It's first law. So now they go to the second law. Now second law is considered that how fast, how does the if that's so, does each planet keep the constant velocity or not? That is the question. So he spent a lot of time observing during the orbit when planet was close to the sun. Kepler developed a law about this and had no explanation. Oh, that is that is this law. That is so that is you did they actually talk about the second law? Yeah, that's right. Yeah, this is good. It's good. Can you see this area? These two areas are equal. Can you see? So the area, area are equal to B. That is no. That is no. That is a per unit. It's of course it's the same time. You spend the same time. You count down the same time.
Right.
So obviously, what we can say is that, do you think the velocity is the same? This v1, this v1, this v2. Do you think velocity would be the same?
Yeah.
No. Okay, the time is the same. Can you see the distance? What is the distance? The distance is this one. Can you see this is distance? Can you see the distance? And that a distance over here is different. Can you see? This is distance. Can you see?
Yeah.
Much shorter. Okay, much shorter, right? So therefore, in order to maintain the same area, and the velocity must be slowed down. So do you agree? So the velocity must first one must be larger than the velocity 2. Okay.
Yeah.
So that's his law. So basically, velocity is not constant. So the state as a radius vector join the planet and sweep out as equal area, equal length. That's very important. Equal length of time, equal time interval. Okay.
Yeah.
So that is very interesting law, and that is how we eventually understand. But he didn't give explanation.
Yeah.
But his law is very accurate. So actually, that is a good example that you see if you want to study physics, and you will know that experiment play a very important role. The measurement, the more accurate the measurement, and is more closer to the theoretical to the theoretical prediction.
Yeah. Yeah.
Okay, that's the first note. You don't have to do much about it. You just know that that time is the time interval is the same. So delta t is the same.
Yeah.
Very important. Otherwise, you cannot compare. It's the same. So that's something you need to remember. The third law is can be examined. Okay, this question can be asked during the test, because in this case we can. I think we have done that, right? We have proved this Kepler's third law. Do you remember? The period square over the radius cubic is constant for every planet, for all planet. In other words, the time taken longer, okay, the time taken and if the radius get longer.
Yeah.
Of course, without a theory, this is very abstract for people who, if they don't have studied Newton's second law or Newton's another law is Newton's gravitational law. Basically, say if the orbit increase, the radius increase, okay, and the period getting longer.
Yeah.
But it's not proportional. You see, it's not proportional. Basically, period increase slower. Can you see? So basically, what it says is equal to constant. If you want to write this as a function, so what you can say, so the period is proportional. Can we put a constant here? The proportional to the q squared equal to rq. Okay. So t will equal to, can we solve that one? So that would be the constant, again, another constant, different constant. That would be the 3/2, you see?
Yeah.
So it's not linear, it's not linear. If you draw this diagram, this time, this period, this is radius. So they just increase. It's slower than, so if you can write that, that's also equal to k, it's constant, is 1.5, you see, 1.5. Yeah. So it's a bit, it's slower than the quadratic, see? So it's slower than quadratic. So this is quadratic, you can see? This is a t, so this is r, so sorry, this r, sorry, this is r. So this is r square. So this is r square. This is r 1.5. Do you remember? Do you want to try how to prove that by Newton's law?
Yeah.
Yeah. Let's go to whiteboard.
Yeah.
You can try. I mean, I think we have done that. Basically, you need to draw a diagram. So in this case, can we put the sun at the center? Is the sun. And in order to use the knowledge we have studied, so we just assume the orbit is a perfect circle. So you can use the formula in the uniform circular motion.
Yeah.
So now this is Earth. So this is Earth or any planet. Don't have to be Earth. This is just planet. Any planet. Okay. Okay, so do you want to try? Can we say this is their radius? So the radius, so this is a radius. This is radius, and they got a velocity, and they got use different color. So this velocity along the tangent direction. Probably use arrow. Do you want to try how to work out? How to work out how to prove that equal to a constant? How to basically you need to prove why to prove. Okay, basically to prove that t squared over r cubic equal to a constant. So this is one way to describe the Kepler's third law, Or you can say that, or you can say TA, RA, one of the planet, were equal to TB, RB. Can you see? That is two form. It's just like gas law. Do you still remember gas law?
Yeah.
The PVC, so PVT equal to a constant, right?
Yeah.
Or you can say P1, V1, T1. This can apply to two equilibrium state, P2, V2, T2. Can you see? So this is similar. Yeah. So you have two form. Do you want to try? I just give you a few minutes.
Yeah. Yeah.
So this is the radius. There's a radius. That's right. Yep. That is that's how to determine the period. Yep. That's because you're talking about circular motion, right? It's a uniform, uniform circular motion. Can I put a label here? Get you put the you're still doing. You substitute, right? Okay, fine. You do this way. Okay. Can we put the equation 2? TR.
Yeah. So equation 1 into 2.
Oh, well, yeah, but yes, go on. But you still got a velocity here. Can you see? We have the velocity here. How can you do that? Try it. Try it. Yeah. But yeah, I think you have to. You will have trouble. I think.
Yeah.
Because you. You see, velocity is there. Can you see? We got a velocity. That's trouble. We'll have trouble. Can you see? There's a velocity here. We can't just substitute. We got R. We got T square. But in this one, there's only have the T and R. Think about it. What is the force? When you solve the mechanics, you have to consider force. Without a force, how can you solve the problem? It's a force. Okay, what is a force actually? Without a force, how can you solve the problem? So what is a force? What is this force? What is a force? Acceleration and a centripetal force in this case.
And the the square of R.
What is the name for that force?
Newton's second law.
No, it's not Newton's second law. You have this is Newton's second law. Can you see? You have
Yes,
Newton's second law already. This other law. Oops, sorry.
Centripetal force.
No, it's not the law. So you have used both. Can you see? When you write it down here, you have used this is come from Newton's second law plus the central the formula for this. So these actually contain the two.
Yeah.
Contain the two formula here. So this got one is Newton's second law. Yes, you are right. You can start with Newton's second law. Another is the formula for the centripetal. So the centripetal acceleration formula. Acceleration. So you already use the two formula to obtain that one.
Yeah.
Anything else? Anything else? Any other?
Gravitational force.
Yes, of course. Yeah. If you don't consider gravitation, nobody can explain this formula. Nobody, without considering force, even Newton. You see, Newton got the three law for mechanics or law of motion, but also he got additional law for the universal gravitational force. That is a key.
So would that be equal to centripetal force? Or?
Yeah, in this case, apart from this, for any other force, can you imagine any planet like Earth, any other force acting on the Earth? Or you can consider Mars. Okay, this is Mars, but Mars is very small. This is Mars.
Yeah.
But compared with the Sun, this force is so weak, so you don't have to consider force. Yes, there is a weak force. Certainly, there is a weak force to the other planet. So that therefore, Newton was clever. Okay, Newton allowed people to solve the problem by using just one gravity, which is relatively speaking is the strongest.
Yeah.
Okay, in this case, you don't have to consider the interaction between the mass. Okay, but it exists. Can you see? There's always attraction. So Newton's universal law say any pair of object with mass, then there exists the attraction. It's called gravity. Okay, can you just continue how to write this force? You don't have to consider the force between Mars and the Earth.
Yeah.
That's right. Yeah. That's right. That is, I put a mass there. So the Sun has larger mass with capital M. Yeah. Earth has smaller mass. Planet has smaller mass, relatively speaking. Yes, nearly there. Nearly. Oh, be careful. How did you get M square? M should cancel. Do you agree? Small m.
Yeah.
Good. You can say R cubed. So that is a capital M, right? Oh.
Yeah.
This is capital M. The M cancel. Yeah, this is capital M. Yeah. Okay.
Yeah.
Yeah, nearly. Almost done. Can we just rearrange that? Follow this. Can when you prove something, you have constantly look at what is the formula they're trying to prove. Okay. Yeah. Obviously, T and R are dependent. They are two variables. Okay. This apart from that, others just a constant. Number are constant. Yeah. Pi are constant. Mass is constant, right?
Yeah.
Yes, you have look at the form. That's right. You look at the form. You're going to prove. Yeah. All of them, including gravitational constant, they all get a constant. So that's proved. Okay, it's good. I think we have done that. You forgot.
Yeah.
Okay. All right. Any other question? Can we ask another question? This is 3 law. That's all. That is the 3 Kepler's law. The first law. Yeah.
The third one. That's okay. This is the third.
This third law, yeah. What you prove, just proven is third law. Do you want to return to your textbook?
Yeah.
Well, do you remember last time we just solved the a binary star, right?
Oh yeah. Yeah.
Yep. So this is similar. Do you think that law can be applied to the binary? Do you think Kepler's law, just in passing, do you think that can apply for the binary star, Kepler's third law?
Yes.
How can you prove that? Can we go back? Can you prove that?
Yeah.
It just occurred to me because it's interesting. You see, Kepler does have this, but he didn't deal in his time. He didn't deal with binary star, but just for fun, okay? Because it's part of circular motion. Can we just do that again? So basically we say if this circle, they got 2 planets, like a 2 planet. So 1 planet here, 1 star. You can have 2 star or two star. You can have 2 star here. Same mass. The mass is the same. The mass is the same, and it's orbit. Okay, the orbit about each other. And the only thing not moving is their mass center in this case. The mass center is not moving because the sun is too heavy. So we can say that the Earth, the mass center is very close to the sun. That is why we just assume that the sun is fixed. So this is mass center. This is mass center. Also, that is the center for the circle. All right, you want to prove that? Question 2. Can Kepler's third law valid? Can it be applied to a binary star? Okay, try it.
Yeah. So, what's big M? Is it a big M?
Or it's just M. The mass are the same. We just make it simpler because if mass is the same, the orbit is more complicated.
Yeah.
Do you want to see what happens? Yeah, well, after that, I tell you what the orbit would be looking like if the 2 masses are not equal.
Okay.
So how can we obtain the radius? How do we obtain the period? We still have to consider that. So in this case, this is the radius. Can you see the radius?
Yeah.
So same velocity. I think it's okay. What do you think? Just intuition. Should be. I think Kepler's third law still can be applied.
Yeah.
Do you want to write something? Yeah, that's period. You can still use period. Yeah.
Can I just start from the third law, from the law?
Oh, you use a third law. Oh, you prove no. You just use this scenario to prove that law, or you can you want to from start law. Yes, you can go either way. Yeah, you can go either way. You can if you. But what you're going to compare if you use third law? Oh, go on. If you just come, you can assume this law is have been proved. Okay, you don't have to reprove that.
Yeah.
Yeah. Well, you see, when you prove that, also in the meantime, you also check. You have already checked whether this is valid. Whether this particular law is valid for this binary stuff. So you can use it. Yeah, no problem. You can use the formula itself, the law itself. Okay. But you have to indicate what is the difference between the sun, the first example. This is there's nothing at the center. It's just the position of the mass center. There's no orbit. There's no star. There's no material at the center. I think you can start from the first one. You don't have to use the Kepler's law. You just eventually, if you have proved that t squared divided by r third cubic equal to constant, then you proved.
Yeah.
Aha, be careful. It's which is r? Which is r? What is the distance between the two planets? Between the two stars? It's different. Can you see? This distance is distance between the two stars. Yeah. Yep, that's good. 3 formula.
Yep.
Yeah, you got a 3 formula. Yeah. I think another formula you need to specify is that in this case, Fc equal to Fg. All right.
Oh, yeah.
Yeah. Yeah, it's basically the same, isn't it? Apart from the constant 4 here. Otherwise, it's the same, okay?
Yeah.
Yeah, we can stop here, but I just want to show you there's another way to see, same problem, but I give you a short. Why don't we start from this one? So this is another method. So alternatively, you can see the method 2 is quicker. So what you can do is you can say because the Fc equal to ma, okay, that is Newton's second law, right?
Yeah.
AC. So therefore, we can, and Fc is given. So Fc is Gm. In this case, m squared, okay, 2r squared will equal to m, right? And that's
Yeah.
v squared, and this is r, you see?
2
Is that right? R squared,
2r
yeah, r squared.
b yeah over 2r because it's
Over
2.
2r. No. the radius is still radius, okay? The orbit, they do the circular motion. They're doing, each of them doing a circular motion. They didn't orbit. This is different. See, the sun is that this. If this is sun, can you see? Be careful. If this is the sun, let's go back. Can you just go back? Can you see this is sun? Can you see? The sun doesn't move. So the sun doesn't move. So the sun is not moving. Sun is still. Of course, it's approximation, okay? Because to some extent, sun will be a little bit change a little bit. Because why? Because the mass of the sun is larger than mass of Earth. Now, in this case, you have to be careful. This is R. Can you see this is R? Can we simplify that? We just simplify that. You just get Gm and 4R equal to mv, v squared. Okay. Okay.
Yeah.
So you can even substitute this equation. So this is equation 1. This is equation 2. Can we just do that? Can you just substitution 1, 2 into 1? Is that quicker? You see the Gm 4R. Can we, this is M have cancelled. See, this M has cancelled. We cancelled one of the M. We have cancelled one of M, right? So that's V squared. That is 4 pi. So it's 4 pi constant. 4 pi is constant. R squared T. Can you see?
Yeah.
So you just do some arrangement. You get, say, you get arrangement. So you got T squared. Oh, this is T squared, right? It's T squared. T squared. Yes, T squared. So you do some arrangement. You go to T squared and got RQ and put the all constant on the other side. Okay, that is 4 pi squared multiply 4 divided by Gm, and you could constant. Yes.
Right. If wait, so for the gravitational force for R, you had 2R.
Oh, they cancel. Can you see? Didn't notice that? I just drew it. These are canceled. Can you see?
Yeah, but if you have 2R there, why don't you have 2R for the centripetal force?
Where? Let's double check that. What did you say? Which which is where is your concern? So this is starting. This is force. Can you see?
Yeah.
So that's 4 because we have R left. Okay. This R square come from this formula because V square. We have V square left here.
Yeah, but
yeah, go on.
Why isn't this one?
Yeah, can you write? Yeah.
I'll write.
This just become 4 times R square, right? 4R square.
I'll just use my.
Can you write?
For this one, why doesn't it become 2R as well?
Let me see. Oh no, it's not 2R. No.
Isn't it the radius between
No. You don't put 2 there. I didn't put 2 there. You don't have to. As I said, because this is just a 2 object moving about a center. Can you see?
Yes.
The formula just pick up one of them. Okay, we pick up one of them. Therefore, the radius must use this distance, not that is their distance between the two stars. You have to use this distance. This is the radius, can you see, of this circular motion.
Yes.
So therefore, that's acceleration, centripetal acceleration equal to the velocity squared divided by r.
But for this one, we have to use
Yeah.
2 for gravitational force.
Oh, that's Newton's law. This distance, you see. So don't this is not, this r is different. This is r is different. This r is different from this one. In Newton's law, the r is the distance between the two objects. Can you see?
Yeah.
Interesting. So the Newton's law. So Newton's law says m1, m2, right?
Yeah.
And that is the distance. Most important. Can you call the d here instead of the r? So Newton's law says that gravitational force is equal to g m1 m2 divided by d squared. Okay, d for distance.
Yeah.
So therefore, but in many cases we just use r. We just assume that there is the center. This is distance from object to the center. After all, this is center. Do you agree?
Yes. Yes.
So this is all right because these are, in this case, this d equal to 2r. Can you see?
Okay. Yeah, it's just confusing.
No. You can see this distance. Can you see this Newton? If you want to use this Newton's law, okay.
Yeah.
This is Newton's law, and this is also Newton's law. But bear in mind these two r are different. Can you see?
Yeah.
This r is not, so you kind of say, so basically this is just f equal to this formula. Can you see?
Yes.
So therefore, do you agree that the force between these two stars is determined by their distance, not halfway?
Yeah.
I know what you mean. So basically, this is all right. In this case, the gravitational force is equal to g m times r squared. Okay.
Yeah. Yeah.
Because this is distance between the two objects. Can you see? In this case.
Yeah. Okay, that makes sense. Yeah.
There's nothing inside. So you have to consider the interaction between these two objects.
Yeah. Okay. Yeah.
That's one way. Can you see this is more effective? This way is faster. Can you see this way?
Yeah.
So you start. So please start from Newton's second law. All right.
Yeah.
Let's go to your whiteboard. Let's stop sharing. Yeah, Sherry, look at your textbook to see if any other question. Yes, the solution. Yeah, that's just numbers, huge numbers. When you're dealing with huge numbers, yeah. They just want you to check, right? You want to check if this is true, or you want to predict the radius. What you're trying to do? A Saturn or the satellite launched into orbit of Earth, around Earth, moving that is a neutral Saturn. Also, actually, Kepler's law also apply for the satellite. Do you know why? Do you know why?
Because the way it orbits is similar to
no. The force, not all. The force determines this ratio. Okay, Kepler's law, actually Kepler's third law implies a force. Okay, that's why in history there is dispute between Isaac Newton and Hooke. Hooke said he's his first person. He claimed that he knew this law before Newton. So because that is possible, because if you assume it's a circular motion, we can use Kepler's third law to derive the formula for the gravity. It is logical. You see, logical connection has no. Basically, when you're dealing with logical, it can be reversed. Okay, you can go backward and forward, unless the process. If you study the chemistry or the physics, thermodynamics, you will see some process irreversible. But logical argument are sometimes is reversible. Okay, reversible.
Yeah.
Any question in this case? No.
No, this is
no, it's easy. Too easy because you got a pair of the Kepler's law. So don't. So you have to. I think you have after have studied this physics for a few years. You have to understand. So the force between the object or acting on object determines the motion of object.
Yes.
So this motion, including how fast it moves, okay, and
Yes.
what is in this particular case, they mentioned that how fast they move is also related to the distance between the planet and the sun. But in
Yes.
our last example, we're dealing with a binary star, and there's nothing at the center. So
Yes.
therefore, the distance between the two objects must be the diameter.
Yeah.
Okay. Okay,
Yeah.
go on. You see, that's a good way. Can you see? Can you start here? This is how to start with dealing with this problem. Okay, I think your way is a little bit is unusual. Can we
Yeah.
start from here?
Yeah.
If you know that is if you know that centripetal force if you know the gravity is acting as a centripetal force, you should immediately write this formula according to Newton's law. All right,
Yeah.
and that
Yeah.
will allow you to cancel to do the simplification very quickly. Can you see that?
Yeah. Yeah.
Mm.
Yeah. But when would Kepler's law not be equal to Newton's law? Is there
Oh,
any?
Kepler law is implied. There's Newton's law. Kepler law is an empirical formula.
Mm,
You can you follow me? So basically, what we have proved that basically without Kepler's law, without Kepler's third law, Newton can also predict that. Do you agree?
yeah.
Can you see that's how Newton did? That's how Newton did. Can you see this is exactly what Newton did? Okay, so
Yeah.
that's why they proved that they derived. See, basically in this case, Newton derived Kepler's third law, or
Yeah. Yeah.
he used theory to explain the Kepler's third law.
Yeah. Yeah. Yeah.
But Kepler is not very good at physics. Do you agree?
Yeah.
He's good at mathematics, but if you see, some people can figure out the data by using the formula. This formula is called empirical formula. Empirical. Empirical is not a fundamental formula.
Yeah.
But Newton, this was fundamental, the basic or fundamental. Basic is different. Okay, see?
Yeah. Yeah.
So Kepler's and what other formula including that I can write down here. So this is one of formula. So that's empirical. Another formula is by Hooke. Okay, he says the force is equal to the constant multiply the distance displacement, right?
Yeah.
So and also there is another form is a fraction. Air
Yeah.
resistant fraction. They're all empirical. They are not fundamental, because they didn't consider the interaction one by one. They just assume, for example, this is friction, and
Yeah.
this is friction. Do you say this is a constant times the velocity square, or
Yeah.
sometimes just velocity? So these are all empirical.
Yeah.
However, basic law like Newton's, this is basic law. Okay, the
Yeah.
basic law can apply to any scenario, but
Yeah.
empirical formula can only apply to particular system. That is the
Yeah.
difference. Okay.
Yeah.
So
Yeah.
yeah, two type of formula in physics. In other area like biology or chemistry, then the most formula are empirical. Okay, most
Yeah.
formula are empirical. Okay, any other question? That is how to determine the period, right? You still apply this law here. In this case, that's right. There's an assumption. Can you see whenever you use this formula for velocity, you have assumed something. What is the assumption we have to
Constant.
yeah, constant, right? Velocity is constant. Okay. If velocity is not uniform, then we cannot use this formula.
Yeah.
Do you remember, say, if the A is equal to constant, what is the velocity? If there's a constant of acceleration acting on object, the final velocity will equal to u
Yeah.
plus at, right?
Yeah.
So that's why However, in the circular motion, there's no force acting along the tangent direction. This is something you have to understand. And some people found it difficult. So you can see, when we started circular motion, we have started the acceleration very strangely. The acceleration is perpendicular to the velocity all the time. You see,
Yeah.
acceleration is toward centripetal, means toward the center. However, the instantaneous velocity is perpendicular. So in principle, you cannot change the velocity amplitude. The only thing you can change is his direction. Can you see?
Yeah.
So this is something you have to be very careful. So the acceleration involves the it describes the change in velocity either in their magnitude, in its magnitude, or in its direction. You see.
Yeah.
Because next moment, the next moment, the velocity will change direction. Okay.
Yeah.
So that is why you have to be careful. So you say, well, some people say, well, some people just use the formula. Can you see? They always think about that. Oh, when there's action, there's this formula we can apply. No, you don't have to. For a straight line motion, if the acceleration is along the direction of motion, and you can use this formula. All right.
Yeah.
Another thing is that in this case, acceleration must be a constant. Okay. If acceleration is not constant, this formula cannot be used. You have to use integration. You have to use integration. Calculus. You have to use calculus.
But velocity, for a circular motion, velocity is never constant, right?
Well, it's not constant. The amplitude is constant.
Why do they use, how could they use V equals to S over T?
Oh, that is magnitude. We derived this formula from this is constant. We derived from formula. Do you remember? We have drawn the formula. We have two triangles. Do you remember?
Yeah.
We use this triangle. We use this two similar triangle. We can prove that formula. Yeah, that's very tricky, because if you don't have to look at the details, the people get confused. That if you just look at the amplitude.
Yeah. The
question problem solving. Yes.
Question 10.
Yeah. The mean radius. So basically, because the ellipse, right? So therefore, they call the mean radius. So in other words, they just deal with as a circular motion. The orbit of planet X in another solar system is a mass and its average value. For this is this one. Determine the period of planet.
That's easy.
It's easy. Okay, simple. Yeah. You see, sometimes it's very silly. Sometimes they just ask you to apply the formula, okay, to plug in the numbers, and but also you have to be careful. Sometimes you have to unify the unit, right? You have unified the unit.
Oh, and T period in this case, is it still in seconds?
Of course, of course. Yeah. You see, period must be saying when you study wave. And when you study the time, no matter which is a time interval or it's a period, it is all use a second. Yes, otherwise you get confused.
Yeah.
For example, how about the unit for the wavelength?
Meters.
Yes, that's right. Because length, can you see?
Yeah.
Wave is just adjective. Okay, you are dealing with length. So the unit length is always meters. Okay, it doesn't matter with wavelength or it's just distance between between the two bars. Gravitational wave. Oh, that is something abstract. Yes, this is totally different idea from the Newton's law.
Yeah, this is like extension stuff.
Extension. Yes. Okay. Do you have any questions? So gravitational wave is very strange wave. Okay, It is a wave that imagine it's described by Albert Einstein, and he believes that his description provide more information about the gravity.
But what do you say?
Well, basically, he just says there's no gravity. He just says he says that the space and the time is not flat. Okay, so in Newton's law, we just this is just a very simple case. So basically, in this case, if you have the object, say if the object, for example, object coming, and this says there's a force. Okay, the force that's called gravity. That's Newton's idea. Now, in Einstein's idea, then there's no force, no gravity. This Newton's idea is Newton's idea.
Yeah.
But for Einstein, is different. Einstein is we can talk about if you wish. Einstein's idea is different. Einstein said, well, there's no such thing called gravity. Okay.
Yeah.
That's 1916. Yes, because it's called the general theory. He said, well, the space and time is not flat. Okay, it's not flat. Can you see that?
Yeah.
So that's his idea. They just got from. Have you seen that diagram before? Yeah.
Yeah.
This time diagram. It's not flat. So therefore, no gravity. So therefore, there are two objects. No interaction. Can you say no interaction?
Yeah.
No interaction. That's very. This is against. This is quite it's alien in physics. Okay. There is an interaction, but there's no interaction. There is no interaction. No attraction. No force.
Interaction. Gravity is just going around the dent.
Well, if you can describe the field, if you describe you can get a similar diagram. If you describe do you remember last time talk about the field?
Yeah.
Gravitational field can be written as, in this case, r squared. Can you see that?
Yeah.
So therefore, from this formula, you can also get this similar diagram. You can also, because of traction here, you can also get this type of diagram, similar to the Einstein's. But this is gravity. See, this is G. Can you see?
Yeah.
Or you can also see there's something not flat. But this is different. This is in space time. So this is a space time. You have to, if you want to know Einstein, you have to learn special relativity first. Okay.
Oh, yeah, that's right.
So you just forget about this. Is just general introduction to tell you. So Einstein Einstein says there's no force. Newton says there's a force. Newton believes this is a force. Okay, it's called gravity. Okay. Now, how this new idea, because this new textbook, they have picked up some new latest report, but personally, I don't believe they have observed anything like a gravitational wave, although someone have got Nobel Prize. Okay, because it's so different. So Einstein's prediction is so different from physical world. Yet they use physical stuff to detect that non-physical wave. So that is a big question mark. The big question mark.
Yeah.
And I can tell you something very strange. They spend years to build this is a very expensive apparatus. Okay, can you see that? Kilometers, several kilometers, and do you believe that in just a couple of weeks they got their result? Once you build this stuff, in few weeks they got their result.
Yeah.
It's very unlikely. It's very unlikely. Okay, it's very unlikely. Because there's random. So all these events they are talking about happen at random. Okay.
Yeah.
And but also before this pandemic, actually they have accumulated more than 20 observations of similar events. Okay.
Yeah.
They don't talk. They don't talk anymore. They think, well, because of pandemic, we stop, running these facilities anyway. Yeah. Gravity just knows that there are. If you be asked in this test, you see that gravity have been described by Einstein differently from Newton. Okay.
Yeah.
So Einstein's including the gravitational wave, and this wave is quite different from the wave we know. The
Yeah.
wave
Yeah.
is propagated in space, but it's generated by, it basically it's totally different. Okay.
Yeah.
You just accept this is something. Well, someone believes that they have observed gravitational wave. Okay,
Yeah. Yeah.
that's it.
Okay.
All right, you want to stop here?
Yeah. Yes.
Okay, okay. See you next time.
Thank you, sir. Thank
You're
you.
welcome. Goodbye.
Bye.
Bye.